Thank you very much, Reynold. Thanks, everybody, for coming. As you said, my name is Michael Armbrust, and I'm here to take you beyond SQL and show you how you can speed up all of the Spark jobs you write, even the ones without SQL, by using this cool new interface that we added in Spark 1.3 called data frames. But before we dive into data frames and all of the coolness there, I kind of want to start with a little bit of background about myself and about Spark SQL. So Spark SQL is part of the core Spark distribution, and I believe most of the vendors kind of ship it along as well, even if not all of them are supporting it yet. We added it, it's actually a pretty young project. We added it just a little under a year ago to the core distribution, so it's pretty new. But since then, it's actually become one of the main focuses of Spark development, both in open source and at Databricks. And you can see this is kind of evidenced by the number of unique contributors continues to increase over time. We're actually really excited about the number of people that are constantly adding code to it. And then also just the activity in the project. A lot of the activity is going into Spark SQL, and even some of the commits that we're doing inside of Spark Core are actually today about making Spark SQL faster. And as you can see, the most recent month, February, was actually a huge month for Spark SQL. That's when we added data frames and all of these new APIs. Another thing that I want to mention is, since it was a brand new project that we just added, for a very long time, Spark SQL had an alpha tag on it, meaning that, while we were actually using it in production at Databricks, the APIs were not necessarily going to be stable. We take API stability very seriously in Spark. And so I'm happy to announce that with Spark 1.3, we have graduated from alpha. The APIs that are listed as public APIs will be stable through the rest of the 1.0 release series. And we actually know quite a few people, especially some very large companies in China, that are using it in production to replace some existing Hive deployments. So that brings me to my next point, kind of what is Spark SQL? How are people using it? So one thing that Spark SQL lets you do is it lets you run either SQL queries or HiveQL queries optionally alongside your existing Hive deployments. So as you can see in this example, if you've got Hive tables, if you point Spark SQL at your Hive metastore, you can directly query them without giving any more information to the system. You just kind of tell it, it will locate the tables and all of the metadata, and you can write queries in the language that you're familiar with. And it goes beyond just integrating with metadata for Hive. We actually also support Hive UDFs. So if you're familiar with the catalog of functions that Hive provides you, all of those are available inside of Spark SQL as well. And you can even take your custom UDFs that you've written for Hive and bring them into Spark SQL as well. So this is kind of a very common way is people will take this and kind of either augment or replace their Hive deployments with Spark SQL. A question I get a lot, though, is, do I need Hive? Can I still use Spark SQL even if I don't have Hive? And the answer is yes. Even if you don't have Hive at all, you can still take advantage of the HiveQL language and everything. And in fact, a little bit of a developer tip. If you can, I would strongly recommend always using the Hive context, because the HiveQL query language is actually quite expressive compared to the kind of standard SQL parser that is built into the SQL context. And if you don't have a Hive installation, we actually automatically set one up for you in the local directory. So you don't need to configure a metastore. You don't need to configure anything else. You just need to instantiate a Hive context, and you can have all of the power that system provides. So SQL is kind of the lingua franca for doing data analysis, especially inside of business intelligence. And this is one of the really cool use cases where we see Spark SQL kind of integrating with other tools that people are already familiar with. So one thing that Spark SQL can do is it'll actually put a JDBC server in front of Spark. So these other tools can now have access to all of the data that you're storing in HDFS in formats like JSON or Parquet. You can automatically connect Tableau or Zoom data or Click to this data that was formerly inaccessible to it by using this JDBC connector. So this is actually a pretty common use case that we see people using. But even if you're not just SQL, we actually have bindings in all of the languages that Spark supports, Python, Scala, and Java. And you can kind of seamlessly mix your RDD actions along with SQL queries. So you can kind of run a SQL query that will extract data from Hive, maybe join it and filter it, and then immediately drop into your Python RDD code to do operations that are hard to express inside of SQL. And so, finally, my name is Michael. I will be posting these slides on Twitter afterwards if you want to follow along. And as Reynold said, I'm the kind of initial contributor and lead developer of Spark SQL at Databricks. So that's a lot of SQL, but I have a secret to tell you guys. I'm actually not going to talk about SQL. Don't tell my PhD advisor who's sitting over there. But the not so secret truth is Spark SQL is not about SQL. In fact, when we started the project, we considered not even naming it that. It just turns out, Spark, but with schema, didn't really roll off the tongue quite as well. So we went with Spark SQL instead. And so really, if you're only thinking about SQL, if you're not using it because you don't want to write SQL queries, you're actually missing out on the best part. And so, don't get me wrong, SQL performance is incredibly important to us. And so, as an example, comparing this to previous SQL systems on top of Spark, like Shark, we have greatly improved the performance on kind of, the de facto benchmark for systems in this area, TBCDS. So SQL is very important still, but really, Spark SQL is about more than just SQL. And so what I'm going to tell you about today is how, even if you're not writing SQL queries, you can use the Spark SQL stack alongside Spark to create and run your programs faster. So it's both about developer productivity and the efficiency of your programs that you're actually running. And so some of the ways that you can improve developer productivity are by writing less code through high-level operations and kind of using some of the abstractions that we provide you inside of data frames. And a way you can actually make your queries run faster is by reading less data, by skipping over the data that you don't care about. And really, kind of at the core of this is taking the biggest advantage that SQL has over imperative programming, the optimizer, and providing it to you in your Spark programs. And so I'm going to show you ways that you can kind of, instead of doing all of the hard work of optimizing your data flow yourself, let the optimizer take care of that for you. So like I said, at the core of Spark SQL is this concept called a data frame. So what is a data frame, and how do I use it in my Spark programs? So, kind of at the highest level, a data frame is a distributed collection of rows. So, very similar to RDDs, it's partitioned across the cluster. But it holds this data type called a row that we kind of understand some of the structure about. In particular, each of the columns within the row is named. And so you can tell us which columns you care about, and we can do optimizations as a result. Your functions to Spark SQL are no longer black boxes because we can actually understand that schema information that you're giving us. Now, clearly, this is not something that we in Spark invented. Data frames have been around. And so, those of you who are familiar with R or Python, we drew a lot of inspiration from these languages when we were designing the data frame API. And so we give you kind of the familiar functions that you guys know how to use already for selecting, filtering, aggregating, and plotting. And I'll be showing some of that in my demo in a couple of slides. So those of you who have been following the project may say, wait a second, I think I've heard about some of this before. Wasn't there this thing called schema RDD? And so basically, data frames are the replacement for schema RDDs. Anything you could do with schema RDDs, you can do with data frames. But we decided to change the name for a couple of reasons. First of all, we were stabilizing the API, and we really wanted to pick something that kind of would resonate with developers, that they would understand better than this kind of weird thing called a schema RDD. And the other thing is, it's not actually an RDD anymore. You can get an RDD from it, but it is kind of its own unique concept. And we did this so that we could blend the APIs. If you're very familiar with the RDD API, you may know that there's a Scala one and there's a Java one, and they're separate. In data frames, all programmers on the JVM can use a single interface. And even in Python, the functions line up. So you can kind of use these things seamlessly cross languages. And so for that reason, we decided in Spark 1.3 to change the name to data frame. So now I want to talk about how you can actually use data frames to write less code. A key way is by using it to do input and output. So one of the kind of hallmark features of 1.3 alongside data frames is a greatly expanded data sources API. And so what this does is it lets developers encapsulate the information about how to connect to different data sources, be it JSON or other JDBC databases, Parquet, Hive, MySQL, et cetera, into a package that you can easily use inside of Spark SQL. So any of these data sources can actually just be mounted as tables, and you can query them as though they were natively part of the system. So we built a whole bunch of these data sources into the core engine, but externally, we've also got a bunch of people working on libraries. So at Databricks, we released a library for Avro. We also released a library for reading CSV. Other people have written libraries to read in DBase. And there's work going on in the community to add support for HBase and Elasticsearch and Cassandra and many more systems. So really, if you're reading and writing data from Spark, you should strongly consider using Spark SQL to do that, because it kind of takes a lot of the boilerplate of configuring these different data sources out, letting you do it more automatically. So once you've got the data into Spark SQL, now there's the question of how do I actually process it? So common operations can actually be expressed just as these high-level constructs on top of data frames. Instead of you having to implement them yourself by hand, you just call functions that select the required columns, join with different data sources, and this is kind of a key part. No matter where the data is coming from, once it's into a data frame, you can easily join it. We don't care whether it came from MySQL or whether it came from Parquet. It's kind of easy to bring these things together. Other kind of high-level operations that we provide and optimize are aggregation, like count, sum, and average. I'll be showing an example of that on the next slide. And finally, things like filtering, we'll not only do them, but we'll also optimize them for you. So, as Spark users, or as people who have probably looked at Spark before, you're familiar with the concept of writing less code. So I want to walk through an example here real quick. I've got a list of names and ages, and I want to compute the average age for a name. I want to see, what all the kids are named and what kind of the old people are named. And so this is the Hadoop program for doing it. I won't kind of step through it line by line, but at a high level, you start off with a map function that reads the data in, parses it, converts it into the form you want, and then you have a reduce function that actually adds all of the things up together, brings them together, and then finally divides to get the actual average. So it's a lot of code to compute an average. And as you may know, Spark will make that quite a bit shorter for you. It's basically exactly the same code. It's just a more expressive API that lets you kind of write it with fewer lines of code in an easier to understand way. But still, that's a lot of code for computing an average. And there's a lot of ones and zeros because I have to name columns by ordinal instead of by name. And so it's actually kind of hard to decipher what's going on here. Like, what is 1, what is 0? And so if you look at this exact same function written using data frames, it's quite a bit simpler and quite a bit easier to understand. First of all, I read from the people's table, so I don't have to worry about data input and output and what the formats are. Sorry. OK, there we go. So you read from the people's table, so you don't have to care about what the data formats are. The group by is just expressed as something you do on a column. The average aggregate is built in. And then finally, we're Spark users, so we call collect to actually get the answer. So that's just one example of this. But you can actually, if you want to see the full API, we've got API docs up. These links will work, so you can check those out later. So, but it's not just about writing less code. It's actually also about having faster implementations. A question I get a lot is, how much of a penalty am I paying for using Python instead of Scala? And the nice thing is, when you write operations in data frames, it's the same execution, the same optimized execution engine underneath the covers, no matter what language you're writing in. So in this example, this is basically the average example from the previous slide. But if I do it in Python, the interpreted language is a little bit slower. I pay a penalty for that. If I write a naive implementation using RDDs in Scala, still not very fast. But if I write it with SQL, Python, or Scala on top of data frames, it all compiles down to the exact same thing, executes using our kind of highly optimized execution engine. So this is a great way for you to kind of just speed up your Spark programs while making them easier to understand. So what I want to do now is I actually want to dive in and kind of show you some real operations on data frames. Let me pull up my web browser here. So what you see here is Databricks Cloud. You've probably heard about this so far in this conference. But everything I'm doing can be done inside of an Apache Spark shell. I just prefer typing code into a web browser because it's a little bit more expressive. And what I'm going to do is I'm going to start with a data set. So I've actually gone on GitHub and pulled down all of the commits to Spark, and I've got a JSON file that actually lists all of those. So you can see I've got my JSON data here. It's just stored out on S3. And what I want to do is I actually want to load that in. So one of the cool things about data frames is we now have this universal load and store function. So basically, any data source that works with Spark SQL using this API, even the external ones, can be called just by calling load, passing it a path to the data, and telling it which data source to use. So in this example, I'm using JSON, but this could be Avro or Parquet or even JDBC or some specialized connection to Redshift, whatever you want. And what the data frame does is it actually goes out, reads that JSON data, automatically infers the schema. So you can see it's figured out all of the columns and all of the names. I can maybe make this a little bit bigger. So it's figured out all of the names and all the types for all the columns. I can even get kind of a tree view of this if I've got a hierarchical schema. And so what you'll see is it's actually preserved arrays and other complex structures that exist inside of my JSON. Those are all still there and can be queried inside of SQL. And once I've got that, I can now run operations on it. So I can do df first, and we'll pull out the first entry of the data frame. I can select individual columns, select df-auth. So I can pull out the individual author name. I can do filters. So if I do filter, author name, get one there. Oh, keyword, oh, equals equals. And so that's a commit that I made. You can do aggregations. So if I want to do a count, it'll show me that. You can see how many commits I've done. So these are commits I've authored. And then you can easily kind of switch it around and change. So if I do committer name. So you can see I actually spend quite a bit more time reviewing other people's code than writing code these days. So cool. So that's kind of a very simple example. But another thing you can do is not everything can be expressed as a data frame operation. Sometimes I want to take my own code and run it inside of data frames. So in this example, I've written a little bit of Python code that does a regular expression to extract out the domain from an email address. So if I run this here, you'll see it took my email address and pulled out Databricks. But I want to use this inside of my data frame. So I'll create a function, get domain. It's going to be a UDF. I'll turn this code up here into a Lambda function. And I can just cut and copy this here and replace this with the column that's coming in, make it tolerant of bad data. And now I've defined a UDF. So if I want to use this on the data frame, all I do is the exact operations I was doing before, a select, and I can actually just kind of inline call get domain and pass it things, fields from the data frame. So committer email. So you can see it actually pulled that out. So, and then, of course, we can do complex aggregation. So let's say we want to know statistics about all of the domains that are actually making commits to Spark. So we'll do a group by, and I'll give a name to this column. Group by domain, and then I want to count. And I only care about the top committers. So we'll do an order by count. And let's just take the first 5, for example. So now you can see the top domains that are making commits to Spark. So Gmail is very popular. And you can see the Berkeley roots here in the project as well. And so that's kind of an example of kind of how you can simply read data in and start doing operations. But really, this is about integrating with other systems as well. So a lot of people are very familiar with pandas. It's a great library for doing plotting and other sorts of things in a very powerful way. So I can actually take this data frame that I just did and convert it to pandas simply by calling the toPandas function and create a plot. And so this will actually kind of plot that information using all of the complexity that pandas allows you to do. Cool. So let's go back to the slides. OK, so that's kind of how you can write less code and make your code faster. But really, a trick when you want to do really fast big data processing is to skip over data that you actually don't care about at all. So the fastest way to do big data processing is to just actually never read the data at all. And Spark SQL can actually help you do this in quite a few ways using a bunch of optimizations that we've built into the system. So one example is just by converting the data to a more efficient format. A very common use case that I see is, JSON is a great interchange format. It's self-describing. It's easy to read by humans. It's very slow to parse. So what people will do is they will use Spark SQL to read their JSON data and convert it into Avro, which is a much more compact binary format. Now I just have to ship less bytes from HDFS or S3 to Spark in order to do the processing. Also, decoding it is quite a bit faster because you don't actually have to do all of the string munging along the way. So that's kind of one way you can read less data. But kind of even more advanced is using kind of columnar formats like Parquet. So most data actually has a whole bunch of columns. And in any given analysis, I only care about some very small subset of these. If you convert your JSON data into Parquet, when you tell which columns you want to read, we automatically configure the Parquet reader to skip over any columns that you don't care about. Parquet contains an index at the bottom of the file, so we can actually just jump to the bits of data that you care about. This can actually really greatly speed up a lot of your queries. Another trick that people will do a lot is when they have a bunch of data, they will group it in folders by time, for example. So a common format you'll see is you'll see a bunch of different directories broken down by year and then broken down by month, and then you actually put the data inside of those nested folders. So, Hive supports this through explicit partitioning, and we also support Hive's ability to do explicit partitioning. But as of Spark 1.3, if you actually just point us at a directory with this structure that's storing Parquet data, we will automatically scan the tree in parallel, figure out all of the different columns, and then kind of automatically infer the structure of this. And when you write queries that have predicates against these columns, we will automatically figure out which folders you need to read from. So this is another way you can really speed up your data if you're running queries only on the last month or only on the last year, but you've got quite a bit more data than that. And then another advanced thing we have is data skipping. So this is a feature that we're working on right now. You have to turn it on by a flag, but I'm hoping to turn it on by default in 1.4. When you use some of the formats like Parquet, even if you don't partition your data, we will keep statistics about each of the columns. So if you've got a year column inside of your data, we'll keep track of the minimum and maximum value. So if, for a given file, the maximum value is 2013, and my query only cares about data from 2015, we know when you run a query, just skip that file entirely. So we start by reading all of the summary statistics, and we'll skip any data where the statistic tells us you don't care about it based on predicates that you've expressed in your computation. And finally, the data sources API actually gives developers who are writing custom data sources even more power to kind of push this information into their own system. So for example, if I'm connecting to Redshift, and I don't want to transfer data that I don't care about, when you write a Spark SQL query against the Redshift data source or the JDBC data source, and it contains predicates, we will convert those predicates into SQL queries that get passed down to the other system. And so basically, you can kind of let that system do what it's good at, then bring the data into Spark to be joined with other data sources. So all of these allow you to read less data, and as a result, make your Spark program significantly faster. So at the core of all of this I'm talking about is this thing called the optimizer. This was actually the first part that we built. It's called Catalyst. And one of the really kind of nice things here is if you write SQL queries or if you write data frame operations, these are all going through exactly the same analysis pipeline. Basically, both of these are just ways to construct what we call a logical plan. So you can think of a logical plan basically as describing the data flow of your computation in a high-level way where we actually understand which columns are being read, what the predicates mean, and it's that extra semantic information that allows us to do quite a few optimizations. And so, once we get that logical plan, part of our process for actually executing this as a Spark job is going through this physical plan selection. So you see here, kind of where we have this physical plans, there's actually a bunch of different possible physical plans that we consider. And then based on the estimated cost of that physical plan, we will choose the cheapest one automatically. And what's really nice is the cheapest one might change as your data changes. So if a table gets larger or you switch a format, we will, without you changing any of your code, automatically pick a better plan for you. So one kind of point I want to make is that, unlike in the traditional Spark DAG, because we have this extra logical structure, optimization can actually even happen across functions. So I can have a function that's doing some kind of join or aggregation, and much later, away from this function, have a filter, and that filter can actually be pushed all the way through that, allowing you to kind of filter data early and do less work. To make that a little bit clearer, let me show you kind of a concrete example. So this is maybe some ad tech or some other kind of machine learning that you're trying to do. And basically what I've done is I've written a library function that takes some stream of events, and using data frame operations, it adds to that stream of events demographic data that I need for the machine learning features. And so kind of basically what you see here is I've got this function add demographics. I join it with the users table, some data that's coming from Hive. And then I also run another UDF to kind of add more information. I want to take the zip code that Hive gives me and translate that into a city name. So because this is data frames, I can just pass in any data frame to this that has the required columns user ID. And it will automatically return another data frame with all of the information you need. And so then I can actually use this. So in the next line, where the orange begins, I take events. I load some data from some JSON data that's stored off on HDFS. And I pass it to this function, returning a new data frame that's got the event stream. And then finally, I'm ready to actually do my machine learning. So I'm going to take this events, and I'm going to filter out two things. First of all, I only care about New York, so I'm going to filter out all of the cities other than New York. And second, I only care about the timestamp column. I'm doing some kind of temporal analysis, so none of those other columns are important to me. I'm going to filter them out, and then I'm going to collect that so I can actually use it for my machine learning. So initially, what this plan looks like is this thing that you see here. So the filter is up above, but really I want to do it earlier. And the reason is this join is very expensive. I'm joining a whole bunch of users who don't live in New York that I don't care about. So I'm wasting a lot of time for data that I'm just going to throw away. Because we understand the logical structure here, what Spark SQL can do is it can actually push that filter down beneath the join, only join on the relevant users, and you'll actually end up running your program quite a bit faster, even though the author of this function never thought about filtering. And kind of even cooler if I do a little bit more optimization of this. So, I was running on JSON initially. That was while I was developing, and I wanted things to be easy. I convert that format to Parquet, and I change my Hive table to be partitioned, and Spark SQL, without you changing any other code, will automatically re-optimize this to take advantage of column pruning and filter pushdown in these data sources that now support it. So because of the kind of power here, one of the things we've done is we've actually used this as the system for doing machine learning pipelines. So this is another feature in Spark 1.3, where basically what we wanted to do is we wanted to make it easy to compose different machine learning functions that you would perform. And what we're using is the common abstraction to pass this data throughout the system is data frames. Well, we get all of the nice optimizations that come from that system. So that's my talk. It's basically with Spark SQL, you can create and run your Spark programs faster, write less code, read less data, and let the optimizer do the hard work. I've got a couple of minutes, and I'd be happy to take some questions if there are any. Yes? So yeah, that's a great question. If I can get my slides back. So yeah, so basically we are really working on performance as much as possible. I have some kind of very preliminary work some very preliminary work. This is the AmpLab Big Data Benchmark. This is with some optimizations that we're working on right now where we improve our shuffle. And what you'll see is that kind of with some of these optimizations, don't believe the FUD that you have to use C++ in order to write a quick database. It turns out you can actually, just by being clever about the way you do serialization and other things, you can get competitive with these systems. So this is very early work, but this is a major focus for the Spark SQL effort. Yes? Absolutely. So let me be clear about this. The current data sources API only supports pushing down filters, but we actually have this kind of experimental hook where you can inject arbitrary query planning rules into the planner. And I actually wrote a mailing list post. If you search for Michael at Databricks and extra strategies on Google, you'll probably find it. And what I show is a way you can write your own catalyst rule that can understand arbitrary logical plans and kind of shift them into whatever efficient operation you want to do. And kind of my goal here is this is an experimental unstable API, but if people do cool things with it, I would love to make public versions of that will be stable. Yes?
You mentioned that the file structure, the structure of your files on disk can be used to partition your data frame.
Yep.
Is that true for like S3 or is that only for local files?
That's totally true for S3. We all, in fact, all of these examples and pretty much a lot of the stuff we do at Databricks is all off of S3, so that should all just work. Yes? Semi-structured. So the question is, do we support semi-structured data? And yes, totally we support semi-structured data. That's part of the JSON stuff that I demoed. Basically what we have is we have the ability to do schema inference over the semi-structured data, figure out what its structure looks like, and then load it into the system. Do I have one more question?
I have one question.
Maybe the last one.
OK, last question.
Yep.
That's a good question. So the question was, for JDBC, is there plans to be independent from the Hive metastore? So let me unpack that a little bit. So right now, our JDBC implementation is based on the Thrift binary protocol that Hive uses. We will probably not move away from that because I don't see any need to. With Spark 1.3, it is pretty easy to use our native data sources inside of, from a JDBC connection. So you can talk to Parquet, you can talk to JSON, you can talk to Avro, all without actually using any Hive tables. Another trick that you can do is you can actually start the Hive server on top of an existing context, and then you can even see things like temporary tables and RDDs that you've created. Okay, thank you very much.
My mic has on.